We know that noise and decoherence are major problems for quantum computers. Even leveraging the power of quantum firmware, errors will limit the scale of the machines we can build. But the good news is that clever algorithm designers have started to discover new problems which can potentially be solved with noisy intermediate-scale quantum computers, or NISQ computers. Problems that could have a huge impact. So we remain in search of quantum advantage, a demonstration that a quantum computer can solve a useful problem significantly faster than a regular one. For instance, quantum computers can be used to solve problems in chemistry, like understanding the chemical properties of, or reactions between, large molecules. This is because we can build a quantum mechanical model of a fundamentally quantum object, the electrons interacting in a molecule. A lot is lost when we translate this problem to an algorithm run on a classical computer. In fact, make a chemical problem big enough, and we can't say very much about it at all. It intuitively makes more sense to do this quantum modelling on quantum hardware, and formal theories back up this idea. All we need to do is outperform the poor reproduction of the problem on conventional hardware to get a big, practically useful win for drug discovery, biology, and industry. Moreover, using clever tricks to minimize the amount of quantum computation through algorithms called VQE and QAOA, we can reduce the demands on the quantum hardware even further. In these approaches, a lot of the computation is still handled well by a conventional computer. A special small quantum coprocessor, or accelerator, is then used to solve very small chunks that are the most difficult for the regular computer. With these simplified quantum coprocessors, quantum error correction is just out of the question. So leveraging approaches like quantum firmware appears to be one of the best pathways to achieving quantum advantage. Remember, that's the point at which we achieve a real benefit by using a quantum computer to solve a problem we really care about. At that point, everything changes. We stop researching how to build useful quantum computers and start producing them. Based on recent progress, our community reasonably believes that quantum advantage is achievable within the next 5 to 10 years. That's not the end of the story, of course. It's really one of the first steps. We can still look to build exceptionally large general-purpose quantum computers. Getting there will require major advances in hardware system design and combining quantum firmware with quantum error correction to push down error rates as low as possible. We have plenty of work to do over the next 50 years, but with quantum advantage approaching so rapidly, right now is the most exciting time to be working in this field. You can learn more about Q-CTRL's quantum firmware and our tools to build error-robust quantum algorithms via our website. Just learning? Black Opal provides intuitive visualizations. Already a pro? Boulder Opal gives you Python tools to deploy these techniques in real hardware.